Have you ever wondered what makes your phone's camera flash so bright? Or how a TV remote keeps working even after you take the batteries out for a second? The answer is a super neat little component called a capacitor. It's one of the most common electronic parts in the world. You can find them in almost every electronic device you own. They're inside your computer, your television, your radio, and even in the circuits that control the lights in your car. These little guys are everywhere, working silently to make our gadgets do amazing things. They come in all shapes and sizes, from tiny ceramic discs to big metal cans. So, what exactly is a capacitor? Think of it like a very small, very fast recharging battery. But instead of storing energy chemically like a regular battery, it stores energy in an electric field. That sounds complicated, but it's really not. Imagine you have a tiny bucket that you can fill with water in an instant and then dump out just as quickly. A capacitor does something similar with electricity. It soaks up electrical charge and holds onto it, waiting for the perfect moment to release it all in a powerful burst. This ability to charge and discharge rapidly is what makes them so incredibly useful in electronics. Let's break it down. A basic capacitor has a very simple design. It's made of two metal plates placed very close to each other, but they don't touch. In between these plates is a material called a dielectric. This dielectric is an insulator, which means electricity can't flow directly through it. You can think of it as a wall between the two plates. This simple sandwich structure, plate, dielectric plate, is the secret to the capacitor's energy-storing magic. The type of dielectric material used can change how much energy the capacitor can hold, making some capacitors better for certain jobs than others. The next time you open up an old electronic toy or a broken remote control, look for these little components. You might see small barrel-shaped objects or flat, colorful discs. Those are capacitors. They are the unsung heroes of the electronic world, quietly managing the flow of electricity to make sure everything works just right. From the biggest power supplies to the smallest microchips, capacitors are there, proving that sometimes the most important parts are the ones you barely notice. They are fundamental building blocks for the technology we use every single day. Consider this. How does this little sandwich of metal and insulator actually store energy? It all starts when you connect a capacitor to a power source, like a battery. The battery begins to push electrons, which are tiny, negatively charged particles, onto one of the capacitor's metal plates. As more and more electrons pile up on this plate, it becomes negatively charged. It's like filling one side of a seesaw with a lot of weight. This buildup of negative charge is the first step in creating our stored energy, a process that happens almost instantly when electricity is applied. Now, remember those two plates are separated by the dielectric insulator? While electrons are gathering on one plate, something fascinating happens on the other plate. The negative charge on the first plate repels the electrons on the second plate. All those electrons on the second plate are pushed away, leaving it with a positive charge. So now you have one plate that is very negative and another plate that is very positive. This separation of charges is the key. The capacitor is now charged, holding a balanced amount of positive and negative energy, ready and waiting. This stored energy doesn't just sit there doing nothing. It creates something called an electric field in the space between the two plates. You can't see this field, but it's a powerful force, like the tension in a stretched rubber band. The energy isn't stored in the metal plates themselves, but in this invisible electric field that spans the dielectric material. The stronger the electric field, the more energy the capacitor is holding. It's like bottling a tiny bit of lightning, holding electrical potential energy in a static state, just waiting for a path to be released. Once the capacitor is charged, it will hold that energy even if you disconnect the battery. It's now a temporary power source. If you then connect the capacitor's two plates with a wire, you create a path for the electrons to flow. The electrons piled up on the negative plate will rush through the wire to the positive plate, creating a sudden burst of electrical current. This rapid discharge is what powers a camera flash or keeps a computer's memory alive for a few seconds. It's a quick, powerful release of all that pent-up energy. Science! So how do we measure how much energy a capacitor can store? We use a special unit called the farad, named after the brilliant scientist Michael Faraday. 1 farad is a huge amount of capacitance. In fact, most capacitors you'll find in everyday electronics are measured in much smaller units, like microfarads, a millionth of a farad, or even picofarads, which is a trillionth of a farad. A 1 farad capacitor would be the size of a large can of soup. The farad rating tells an engineer how much charge the capacitor can hold for a given voltage. The amount of capacitance a capacitor has depends on 3 main things. First is the size of the metal plates. Bigger plates can hold more charge, just like a bigger bucket can hold more water. Second is the distance between the plates. The closer the plates are to each other, the stronger the electric field between them, and the higher the capacitance. Finally, the type of dielectric material between the plates matters a lot. Some materials are better at supporting an electric field than others, which allows the capacitor to store more energy in the same amount of space. Let's talk more about that amazing electric field. This invisible force is where all the action happens. When the capacitor is charged, the dielectric material between the plates gets stressed, almost like it's being stretched. The atoms inside the dielectric slightly reorient themselves in response to the positive and negative plates. This internal stress is the physical manifestation of the stored energy. When the capacitor discharges, the field collapses, and the energy is released into the circuit to do useful work, like lighting up an LED or making a sound. Understanding capacitance is crucial for anyone designing an electronic circuit. Choosing a capacitor with the right farad value is essential. If the capacitance is too low, it might not be able to store enough energy to do its job properly. For example, a camera flash wouldn't be bright enough. If the capacitance is too high, it might take too long to charge or release its energy too slowly for the circuit's needs. It's all a balancing act, and engineers use these values to precisely control how electricity behaves in our devices. Capacitors are like the multi-tool of the electronics world. They have so many different jobs. One of their most important roles is filtering. Power coming from a wall outlet isn't perfectly smooth. It has tiny ripples and fluctuations. A capacitor can act like a shock absorber for electricity. It charges up during the peaks of the power signal and releases energy during the dips, smoothing out the ripples and providing a clean, stable stream of power to sensitive electronic components. This ensures your computer or phone works reliably without crashing. Another cool job for a capacitor is timing. Because it takes a predictable amount of time for a capacitor to charge and discharge through a resistor, engineers can use them to create timers. Have you ever noticed how the light on your computer stays on for a few seconds after you turn it off? That's likely a capacitor at work. It slowly releases its stored energy to power the LED. This timing property is used in all sorts of circuits, from blinking holiday lights to the oscillators that create the clock signals that run our computers. Capacitors are also used for something called signal coupling. In an audio amplifier, for example, you want to pass the alternating current signal of the music to the next stage of the amplifier, but you want to block any direct current that might interfere with it. A capacitor is perfect for this. It lets the alternating current signal pass through while blocking the direct current. It acts as a gatekeeper, ensuring only the right kind of electrical signal gets through. This is why the sound from your speakers is so clear and free of humming or buzzing noises. From storing a quick burst of energy for a flash to smoothing power, timing events, and filtering signals, capacitors are absolutely essential. Without them, our modern electronic devices simply wouldn't work. They are fundamental components that allow engineers to control electricity with incredible precision. So the next time you use your phone or watch TV, take a moment to appreciate the millions of tiny capacitors working behind the scenes. They are a brilliant example of how simple principles of physics can be used to build the amazing technology that powers our world. Now you know.